Okay, today we're looking at merge k-sorted linked lists. This is the last linked list problem in the Blind 75, and then we'll move on to trees. And this is also the only hard linked list problem on the Blind 75. Unfortunately, it's at least the solution that we'll go over today is not super involved as far as linked lists goes. It's actually more of a heap problem, which we'll talk about a little bit, but let's dive right into it. Okay, so the problem prompt here, you are given an array of k linked lists, that's called lists, where each list is sorted in ascending order, and our job is to return the sorted linked list that is the result of merging together all of these individual pre-sorted linked lists. So you can see, again, it's not really an array, it's actually a linked list that comprises of the nodes 1, 2, and 4, and then 1, 3, and 5, and then 3 and 6. And the output is just this linked list that has all of those nodes in order. When there's equal elements, like these both have a 1 in front, it doesn't matter which one we put first. So we just need to have a linked list that ties together all these nodes. So this guy will point over here, which will point over there, which will point over here, point over here, point over there, point over there, point over there. And then we will return whatever the head of the list is. Okay, and they give us a couple of clarifying examples here. If it's an empty list, so there's no lists contained at all, we can go ahead and just return none in this case, not an empty list, but none. And then if we have a list that has got an empty list or maybe multiple empty lists, we will also return none in that case. Okay, and then the constraints here, the length of lists. So the number of lists will be between 0 and 1,000. The individual lists will have between 0 and 100 nodes. And then lists ij. I think this is supposed to say lists ij dot value or dot val will be between -1,000 and 1,000. So we won't manipulate those, and they seem like well-behaved numbers, so we don't have to worry too much about that. So yeah, the logic for this is pretty straightforward. When it's a small list, right, we just find whatever the smallest front node is, and then if we connect a node, we'll have the kind of front, so to speak, of that move forward so that we're considering the next thing in that list. Yeah. So let's talk just the tiniest bit about heaps here, because it's the data structure we'll be using today. We've actually touched on heaps a little bit before, but just as a little bit of a reminder, the way that a heap works, we can think of it as a tree structure, where depending on if we're using a min heap or a max heap, this example will be, well, let me think. We want a min heap for this problem, which also just so happens to be the implementation that Python chooses by default. What this means for us is that any particular node is smaller than both of its children. And so we have this tree structure. Maybe we've got something like 2 here, and 3 here, and 5 here. Oh, I don't know why that one's an oval. And a 5 here. And this is true for the children nodes as well. So this guy might be something like, maybe it has 4 and 7 as its children, and so on and so forth. Maybe this guy has an 8 over here. And so the quality that is true for every single node in this tree is going to be that the node itself is smaller than both of its children, right? The advantage of this, it's a few things are helpful about this. First of all, the way that, or the benefit, one of the benefits this confers to us is that it's very easy to pick the minimum most element. Because if this guy is smaller than its children and its children are smaller than its children, then we know that the absolute smallest node in the tree has to be the one right here. Okay, and this is inverted for a max heap. We'll be dealing with a min heap today, so we'll kind of keep rolling with that example. The other benefit of this is that anytime we want to remove or add an element, and we won't go over all the intricacies of how this works because we're just sort of engaging with it as a tool. But the other benefit is that adding a node as well as popping the root both occur in time complexity O of log n. So we don't have to if you think about what would happen for a list, if we needed to insert an element, we might potentially have to put it at the front and then push everything back, which is O of n, right? If we have to pop the front element of the list, that's going to be O of n. And the benefit of the heap is that it's just O of log n to do either of these operations. And this is pretty much all we need to do throughout this problem is like add a node, which would be like if we're picking the minimum from that list, then we need to put the new node in or the next node in. And we always want to be keeping track of what like the minimum most node is, which again is sort of the key personality trait, so to speak, of a heap. Okay, so yeah, these three operations, like getting the root or popping the root, I guess it's really just two operations. Popping the root and adding a node, that's exactly what we need to do throughout this problem, so that's what we'll do. I think really the challenge for this one, once you understand that heap qualities are useful here, is just tracking some edge cases, like what happens if we exhaust a list. How should we store the nodes of the list so that they so that Python's like heap implementation can actually like interact with them. That's sort of the tough part. And I think we're gonna go right to it because again, we got a GBM today, so we're gonna like just jump straight into the code here. But yeah, essentially all we're gonna do is create a heap out of all of like the front nodes or all the head nodes here. That's gonna let us very quickly figure out what the next node in line is. And once we know what the next node in line is, we can just add it to the end of a running list and then grab its neighbor. So if we grab this node, we'll grab its neighbor, put it into the heap, and continue that until we've exhausted all of the nodes. So yeah, actually a pretty straightforward algorithm given that it's a hard problem. But let's think about how to do this. So we talked about this before, but we can create a dummy head node. Since we don't know which list is going to kind of be the front right off the bat, we can say, let's go ahead and make a dummy head node, and we'll just make it a default list node. Okay, and then we'll have like a traveler node that starts at that dummy head, and this is just going to let us always know where the end of like the combined list is. Okay, so what are we going to do from here? Well, Python's heap implementation, actually, we need an import for it. We're going to import heap queue. Okay, and that stands for heap/priority queue. And the way that we use it is we actually basically just use a list. Again, we won't go over all the intricate details of this, but basically the way that the heap implementation works is like we have a node and there's a formula you can use to get its two children. And so basically Python can do lots of fun little like index and list stuff to keep the heap heaped, I guess. Yeah, I don't know why I typed that. We actually don't really need to go over it. Yeah, so anyways, all we have to do is just use a list and call certain functions from this heap queue library to make sure it does heap stuff instead of list stuff. All right, so we'll say node heap maybe is going to be just this empty list at first. And then we can say for, so it's a list of list nodes. So I'll say for node list, no, I'll just say for node, because like these are actually, it's just nodes. Like it looks like a list here, but what's really stored is just the front node, the head node on each of these lists, right? Okay, so I'll say for node, wait, yeah, for no, this is so strange. For node in lists, yeah. Okay, so here's the thing. What we would like to say is something like this. So first of all, the syntax for this is going to be heapq.heap push. So what this means is I want to add something into the heap, and I want to make sure that it still behaves like a heap once I add it. Okay, so we can say heapq.heap push, and the first thing we list is what the heap is. So in this case, it's node heap. And the second thing we put is like the node. Okay, now here's the problem. Python is going to use less than and greater than logic to compare these guys to each other, but there is not a default behavior for a custom class. Like we never said what it looks like to compare two nodes, right? So what we can do to kind of circumvent that, or like kind of align ourselves with Python's functionality here, is we can use a tuple, and in this tuple we can put the node, needs to be there, like, because we need to know what node it is, but in front of it we can put node.val. And so this says store a tuple where the first item is the value of the node and the second item is the node itself. And what Python does is it'll look at the first element of the tuple first and see if there's a way to order it using that. And if they're equal to each other, then it looks at the next thing and it looks at the next thing and so on. So it'll do that automatically, but we need to give it as kind of the first, at least the first, if not a few like elements of this tuple. We need them to be like things that can be compared with less than or greater than. And so node.val is a great option for that because it's just an int, and Python knows how to compare ints. All right, there's going to be one problem with this in a sec. Well, in fact, I guess we'll just talk about it right now. The problem is that basically, like I just said, what Python will do is it'll look at the first thing in the tuple and try and compare them. But if they're equal, it'll try and compare the second thing. And it's totally possible, like we saw in the example, to have two nodes with the same value. So we need to give it some other way of like breaking ties because it doesn't know how to compare these nodes, right? This is a little bit of like a hacky way to do this, but I'm literally just going to say tiebreaker is just going to be this int that every time we add in a node, we'll increment it. So this way, just there's never a tie. We're always going to say like tiebreaker, we'll just automatically say whatever got the lower tiebreaker is going to be the better one. Okay, and again, this is by default a min heap, so it's going to help us grab the minimum element like repeatedly very quickly. Okay, so I'm going to go ahead and implement tiebreaker right here just to increment by 1 every time we add in a node. And there's not really, I mean, you know, Python already is very flexible with very large numbers, but we would have to process like a truly insane number of nodes for this to ever not work. So we'll just let it do this. Okay, so by this point, what we'll have is a heap that contains all of the heads of the lists from here. Okay. Now, the other thing, God, I'm thinking about all the edge cases before I even get to the algorithm, is it's possible for us to have like a none node as one of the lists here. So we don't want to push none because we can't get a value out of it. We'll just say if node. So assuming that there actually is a node there, go ahead and do this. And if it's none, we don't have to worry about it because it's not going to get tied in anyways. It's just a none. It's an empty list. Okay, so there we go. Okay, so at this point, we've got heap that's got all of the head nodes in it. Now, what are we going to do? Well, as long as there is something in that heap, we're going to say, hey, go ahead and give me the minimum element. And here's where it gets weird, is we need to hook up that traveler pointer, or whatever node is at the end of the list right now, to like not the tuple, but to the actual node that sits at the end. So traveler.next is going to be, oh, okay, so we need to get, oh, there's so many things here. Okay. So we need to get the smallest element, which is going to be heapq.heapPop on node heap. So same syntax as before. We're going to say, hey, I need to use this function. I'll give you the heap that I'm talking about right here. We don't need to give it a second thing because this is going to find and remove the minimum element. Okay, but again, the thing that's being stored in this heap is actually a tuple, so what we really need is the node that sits at the end, which we can access just with these square brackets. Okay, and then traveler, is going to move on, but what I'm realizing is after we remove this node, we also need to get its neighbor, right? Because eventually we're going to use like the next thing in that list if there is something there. So here's what I'll do instead. I'll say like min node equals this. Okay. We'll go ahead and put its neighbor into the node heap. Oh boy. but we don't want to if it's none. God, there's so many things to consider here. Maybe this is a hard problem. Okay, so if min node.next, so if there is something else to add from that list, then we will go ahead and push it on, and same kind of behavior as before. We'll put min node.next .val and tiebreaker, and then the node itself. And like before, we'll go ahead and increment the tiebreaker right here. Wow, there's so much going on here. Okay, so Traveler now needs to get the min node. And then it moves on because that node that we just added on is the end of the list now, or the end of everything we've processed so far. And I think that's it. By the time we're done with this, we'll have exhausted all of the nodes. So if there is something else in the list that we just pulled from, then we're going to add another one right here, so it'll kind of balance itself out. And eventually we exhaust all of them and we never add things kind of to the heap, and it goes to length 0. We're out of things to add, and at this point we can just return dummyhead.next. Okay, I probably should have been testing a lot more stuff there, but my brain's kind of fried, so we're gonna see if that worked. Are you guys excited? Oh. Okay, let's see if this bit works. Ooh. Ooh. Never failed this problem. You love to see it. Wow. Have I never done this problem before this? I feel like oh no, that was last year, damn. Okay, anyways, that's what we got. Feels good, man. And literally the board chilling in VC right now, I'm dead. Great, feels great though. Guess we'll call it there. That was really fast actually. Normally there's like a lot more to talk about. Again, it's a little sad. This isn't really like a ton of a linked list problem. It's more of a heap problem, but we still have to do some things like, you know, next checking and kind of working with these as nodes rather than lists and so on. So sweet, we'll call it there. Oh, please tell me I was recording. Oh, I was, thank God. Don't ask you what a heap queue is. It's just a heap, which is an example of a priority queue. Okay, we'll call it there then, and I'll see some of y'all at 7, as well as hopefully more people than just the people here. But anyways, see y'all soon.